What if everything we thought we knew about visitors from beyond our solar system was completely wrong? What if the mysterious object that's been racing through our cosmic neighbourhood for the past several months isn't just another chunk of ice and rock from distant stars, but something far more extraordinary? Today we're diving deep into one of the most controversial scientific debates of our time, centred around an interstellar traveller called 3I Atlas. While most astronomers insist this is simply a natural comet from another star system, one of Harvard's most respected astrophysicists is making claims that have sent shockwaves through the scientific community. Dr. Avi Loeb isn't just suggesting that 3I Atlas might be unusual. He's publicly stating that this object could represent our first confirmed detection of alien technology. Before we go any further, if you're fascinated by the mysteries that challenge our understanding of the universe, make sure to hit that subscribe button and turn on notifications. This story is developing rapidly, with new observations coming in almost daily, and you won't want to miss what happens next. And if you appreciate deep investigations into the most mind-bending cosmic puzzles, give this video a like. It really helps more people discover these incredible stories. So what exactly makes 3I Atlas so different from every other space rock we've encountered? Let me walk you through the evidence that's causing such heated debates in astronomy circles around the world. First discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System in Chile, 3I Atlas immediately stood out as something special. The trajectory calculations revealed this wasn't just another asteroid orbiting our Sun. This object was following a hyperbolic path, meaning it came from somewhere beyond our solar system and was just passing through. Only the third confirmed interstellar visitor we've ever detected, following the famous Oumuamua in 2017 and Comet Borisov in 2019. But here's where things get interesting. While those previous visitors raised their own questions, 3I Atlas is displaying characteristics that are making even skeptical scientists take a second look. The sheer size alone is staggering. We're talking about an object roughly 10 kilometers across, making it approximately 1,000 times more massive than Comet Borisov. To put that in perspective, if interstellar objects were randomly distributed throughout space, we should have discovered 1,000 smaller objects before encountering something this massive. The statistical probability of finding such a large interstellar visitor so early in our detection efforts is astronomically low. Then there's the trajectory itself. Our solar system is essentially a flat disk with all the major planets orbiting in roughly the same plane called the ecliptic. Random interstellar objects should approach from any direction in three-dimensional space. Yet, 3I Atlas arrived along a path that's almost perfectly aligned with our planetary plane. The probability of this happening by pure chance is less than 2%. It's as if something deliberately aimed for the optimal viewing angle of our solar system's main attractions. Dr. Avi Loeb has been meticulously documenting these anomalies, and his analysis reveals a pattern that's difficult to dismiss as mere coincidence. As the former chair of Harvard's astronomy department and head of the Galileo project dedicated to searching for evidence of extraterrestrial technology, Loeb brings serious scientific credentials to this discussion. He's not some fringe theorist looking for attention. This is someone who has published hundreds of peer-reviewed papers and advised NASA on multiple occasions. According to Loeb's analysis, 3I Atlas exhibits 12 distinct anomalies that challenge our understanding of how natural interstellar objects should behave. Each individual anomaly might have a conventional explanation, but when you stack them all together, the picture becomes increasingly difficult to reconcile with purely natural processes. The object's rotation period of approximately 16 hours, combined with its apparently spherical shape, represents another puzzle. Most natural comets are irregular chunks of ice and rock that tumble chaotically through space. But 3I Atlas maintains a steady rotation and shows minimal brightness variations, suggesting a relatively uniform, possibly spherical structure. This is exactly what you might expect from an engineered object designed for interstellar travel, where a spherical shape would minimize surface area and reduce the accumulation of interstellar dust during a journey lasting millions of years. When 3I Atlas made its closest approach to the Sun on October 29, 2025, something unprecedented happened. The object began displaying activity patterns that don't match standard comet behavior. High-resolution images captured by amateur astronomers revealed complex jet structures extending millions of kilometers into space. These weren't the typical diffuse clouds of gas and dust you'd expect from sublimating ice. Instead, They appeared as remarkably straight, narrow beams that maintained their structure across vast distances. Even more puzzling was the orientation of these jets. In natural comets, material gets pushed away from the Sun by solar radiation and the solar wind. But some of the jets from 3I Atlas appear to be oriented perpendicular to the Sun's direction, and in at least one case seem to extend ahead of the object in its direction of travel. This forward-pointing plume is extremely difficult to explain through conventional comet physics. NASA's Mars Reconnaissance Orbiter managed to capture images of 3I Atlas when it passed within 30 million kilometers of the red planet. However, when NASA held their long-awaited press conference on November 19, 2025, the results were disappointingly inconclusive. The images showed what officials described as a fuzzy ball of light, degraded by spacecraft vibrations and motion blur. More importantly, NASA's presentation seemed designed to downplay any unusual aspects of the object, emphasizing that everything could be explained through natural processes. Dr. Loeb was highly critical of this approach. He argued that NASA made two fundamental mistakes with their press conference. First, they focused on what they believed they already knew, rather than highlighting the genuine mysteries that make 3I Atlas scientifically fascinating. Second, they held a press conference for data that didn't provide significant new information, suggesting their primary goal was managing public expectations rather than advancing scientific understanding. The most intriguing detail from NASA's high-resolution image involved the fuzzy glow surrounding 3I Atlas, known as the coma. This extended glow appeared to be elongated in the direction of the object's motion, rather than being pushed away from the Sun as you'd expect from natural outgassing. Even more mysterious, the glow seemed to extend ahead of the object, preceding it as it travelled through space. Loeb proposed a provocative explanation for this forward-pointing plume. If 3I Atlas were a technological object, it might be using some kind of directed beam to illuminate the path ahead, detecting and potentially deflecting micrometeorites that could damage the spacecraft at interstellar velocities. At speeds of 67 kilometers per second, even tiny grains of dust become devastating projectiles. An advanced probe might need active protection systems to survive such a journey. This brings us to one of the most fascinating correlations in the entire 3I Atlas story. During his analysis, Loeb discovered that the famous WOW signal detected in 1977 originated from a direction within 9 degrees of 3I Atlas's trajectory. The WOW signal remains one of the most compelling potential SETI detections ever recorded, a powerful radio transmission that lasted 72 seconds and has never been detected again despite numerous follow-up searches. The angular separation of 9 degrees might seem large, but in astronomical terms it's relatively small. If 3I Atlas was indeed the source of that signal back in 1977, it would have been approximately 3 light days away from Earth, requiring about 1 gigawatt of power to produce the observed signal strength. That's substantial, equivalent to the output of a nuclear power plant, but not impossible for an advanced civilization. This correlation prompted Loeb to immediately contact radio observatories, urging them to search for signals from 3I Atlas. The Meerkat Radio Observatory in South Africa conducted observations on November 5th, scanning frequencies between 0.9 and 1.6 GHz. While they detected approximately 23,000 signals, analysis concluded that all were likely human-made interference. However, this doesn't rule out the possibility of technological origin. The search was limited to specific frequencies and times, and there's no reason to expect constant radio transmissions from an interstellar probe. As we continue investigating this mysterious visitor, one thing becomes increasingly clear. Whether 3I Atlas turns out to be natural or artificial, it's forcing us to confront fundamental questions about our place in the universe and the methods we use to search for evidence of other technological civilizations. The amateur astronomy community has been instrumental in advancing our understanding of this object. While professional observatories were dealing with bureaucratic delays and equipment limitations, dedicated individuals with backyard telescopes captured images that revealed the complex jet structures and unusual tail formations that have become central to the debate about 3I Atlas's true nature. These observations showed something that the blurry NASA images had completely missed. 3I Atlas wasn't just passively drifting through space with a simple, fuzzy glow around it. It was actively exhibiting structured, organized activity that extended across distances comparable to the Earth-Moon separation. The jets appeared remarkably straight and narrow, more like focused beams than the chaotic outgassing typically associated with natural comets. What makes these jet formations even more extraordinary is their apparent stability. In natural comets, as the nucleus rotates, active regions move in and out of sunlight, causing jets to sweep across the sky like cosmic sprinklers. But the jets from 3I Atlas maintain remarkably consistent orientations, as if they're somehow decoupled from the object's rotation, or originating from sources near the rotational poles. Dr. Loeb has been particularly intrigued by what he calls the sideways lines, visible in these amateur images. These linear features extend perpendicular to the expected Sun-comet axis, creating patterns that don't conform to standard models of solar-driven outgassing. Some of these lines appear to trace paths that could indicate smaller objects or fragments separating from the main body, raising the possibility that we might be witnessing a controlled deployment of probes or instruments. The timing of 3I Atlas's discovery also presents an intriguing puzzle. The object was detected in December 2024, giving astronomers months of advance warning before its closest approach to the Sun. This early detection is unusual for interstellar visitors, which are typically discovered much closer to perihelion when solar heating makes them bright and active. The fact that 3I Atlas was already exhibiting detectable activity at such great distances from the Sun suggests either an unusual composition or possibly an internal energy source independent of solar heating. When we examine the object's behavior during its solar encounter, additional anomalies emerge. Most comets undergo dramatic changes as they approach the Sun, with increasing brightness and activity levels that correlate directly with decreasing solar distance. But 3I Atlas displayed a more complex pattern, with periods of enhanced activity that didn't always correspond to its proximity to the Sun. This suggests that factors beyond simple solar heating might be driving its observed behaviors. The non-gravitational acceleration measurements add another layer to the mystery. Natural comets often show slight deviations from pure gravitational trajectories because jets of escaping gas act like tiny rocket engines. However, despite the extensive jet activity observed around 3I Atlas, the measured non-gravitational forces are surprisingly small. This could indicate that the jets are somehow balanced, pointing in directions that cancel out their propulsive effects, or that the object's mass is so large that even significant thrust produces minimal acceleration. Dr. Loeb has developed what he calls the Loeb scale to assess the likelihood that an object might be technological rather than natural. This ranking system considers multiple factors including trajectory, composition, structure, and behavior patterns. While he initially rated 3I Atlas at 4 out of 10 on this scale, he has indicated that the accumulating evidence could push that rating higher as more data becomes available. The spectroscopic analysis of 3I Atlas reveals another set of puzzling characteristics. Multiple telescopes have detected hydrogen around the object, indicating that water ice is indeed sublimating from its surface. This supports the natural comet hypothesis, but the distribution and intensity of these hydrogen emissions show patterns that don't entirely match simple models of solar heating and ice sublimation. The detected water vapor could be consistent with either a natural comet or a technological object that accumulated ice during its interstellar journey. Perhaps most significantly, NASA has been notably reluctant to conduct searches for what scientists call technological signatures. These would include things like excess heat that can't be explained by solar illumination, organized radio emissions, or structural features that suggest artificial construction. The James Webb Space Telescope has the capability to detect excess infrared radiation that might indicate internal power sources, but such searches require active effort and specific observational programs. Loeb has been vocal about this limitation, pointing out that you cannot find evidence of technology unless you're actually looking for it. If your starting assumption is that everything must be natural, if you're not actively searching for signs of artificial origin, then of course you won't find any. This becomes a self-fulfilling prophecy, where the absence of detected technological signatures is used to support the natural origin hypothesis, even when no serious search for such signatures has been conducted. The broader implications of the 3I Atlas debate extend far beyond this single object. We're currently entering what could be called the golden age of interstellar object detection. The Vera Rubin Observatory, scheduled to begin operations soon, will dramatically increase our ability to spot these cosmic visitors. Estimates suggest we might discover dozens or even hundreds of interstellar objects in the coming years, each one representing a potential window into distant stellar systems and possibly into the activities of other technological civilizations. This raises important questions about our search strategies and scientific methodologies. If even a small percentage of interstellar visitors turn out to be artificial, we need robust methods to distinguish them from natural objects. This requires not just better detection capabilities, but also a willingness to seriously consider non-natural explanations when the evidence warrants it. The resistance within the scientific community to entertaining technological explanations for unusual observations reflects deeper issues about how we approach potentially paradigm-shifting discoveries. The career risks associated with proposing artificial origins for astronomical objects have historically discouraged researchers from pursuing such investigations. However, as Dr. Loeb argues, science progresses through the testing of hypotheses, including uncomfortable ones that challenge our preconceptions. Recent developments in the field of astrobiology and CT research have begun to change these dynamics. Projects like the Galileo project are bringing rigorous scientific methods to the search for technological signatures in space. These efforts represent a maturation of the field, moving beyond passive radio searches to active investigation of physical objects and phenomena that might indicate the presence of technology. The case of 3i Atlas also highlights the valuable role that amateur astronomers continue to play in modern scientific discovery. While professional observatories deal with bureaucratic constraints, limited observing time and institutional pressures, dedicated amateurs with sophisticated equipment can provide continuous monitoring and capture crucial data that might otherwise be missed. Their contributions to our understanding of 3i Atlas have been absolutely essential. As December approaches, the astronomical community is preparing for what could be one of the most important observational campaigns in recent history. On December 19, 2025, 3i Atlas will make its closest approach to Earth, coming within approximately 50 million kilometers of our planet. This represents our best opportunity to study an interstellar visitor in unprecedented detail. The James Webb Space Telescope will conduct detailed spectroscopic analysis, potentially revealing the exact chemical composition of the jets and determining whether they contain unexpected materials. Hubble will track the evolution of structures over time, looking for evidence of discrete objects separating from the main body. Ground-based observatories around the world will monitor changes in brightness, rotation, and activity patterns. Dr. Loeb has stated that this observational campaign should provide definitive answers about the nature of 3i Atlas. The data collected during this period will either support natural explanations for all observed phenomena or reveal signatures that can't be reconciled with conventional comet physics. Either outcome would represent a significant advance in our understanding, but one possibility would fundamentally change our perspective on our place in the universe. The implications of discovering our first confirmed example of extraterrestrial technology would extend far beyond astronomy. It would prove that technological civilizations can develop the capability for interstellar exploration and choose to use it. It would suggest that the galaxy might be far more populated with intelligence than we've assumed. And it would open up possibilities for learning from civilizations that have solved challenges we're only beginning to face ourselves. But even if 3i Atlas turns out to be entirely natural, the methods we're developing to investigate it and the questions we're learning to ask will serve us well as we encounter future interstellar visitors. We're establishing protocols for recognizing and studying these cosmic messengers, preparing ourselves for whatever surprises the universe might send our way. The story of 3i Atlas is still being written, with new chapters arriving almost daily as fresh observations come in from telescopes around the world. Whether this mysterious visitor from another star system represents a natural wonder or something far more extraordinary, it's already succeeded in pushing the boundaries of our scientific thinking and opening our minds to possibilities we're only beginning to explore. The scientific establishment's reaction to these mounting anomalies has been telling. Rather than embracing the mystery and encouraging thorough investigation, many institutions have doubled down on conventional explanations, sometimes stretching natural processes to their breaking points to avoid considering alternatives. This resistance isn't necessarily born from closed-mindedness, but from the very real professional risks associated with entertaining technological explanations for astronomical phenomena. Dr. Loeb has experienced this resistance firsthand. His willingness to publicly discuss the possibility that 3i Atlas might represent alien technology has drawn criticism from colleagues who worry about the field's reputation. Some have accused him of sensationalizing the data or jumping to conclusions without sufficient evidence. Yet when pressed, these critics often struggle to provide convincing natural explanations for the full suite of anomalies surrounding this object. The debate has highlighted a fundamental tension in modern astronomy. On one hand, we have the principle that extraordinary claims require extraordinary evidence, a standard that has served science well by preventing premature acceptance of revolutionary ideas. On the other hand, we have the equally important principle that science should follow the evidence wherever it leads, even into uncomfortable territory. What makes this tension particularly acute with 3i Atlas is the quality and quantity of observational data. This isn't a case of a single, questionable detection or a poorly understood phenomenon. We have multiple independent observations from different telescopes, different countries, different research groups, all pointing toward behaviours that don't fit neatly into our existing models of interstellar comets. The forward-pointing plume remains one of the most challenging features to explain naturally. When material escapes from a comet, it gets pushed away from the Sun by solar radiation pressure and the solar wind. The idea that this material would somehow end up ahead of the object, in its direction of travel, requires invoking complex scenarios involving rotation effects, outgassing patterns, and viewing geometry that strain credibility when applied to the specific observations of 3i Atlas. Meanwhile, the technological explanation offers a straightforward interpretation. An interstellar probe travelling at tremendous velocity through potentially debris-filled space would need some method of detecting and clearing obstacles from its path. A directed beam that illuminates the space ahead while simultaneously deflecting dangerous particles would serve this purpose perfectly. The energy requirements, while substantial, aren't beyond what an advanced civilization might achieve. The radio observations conducted by Meerkat and other facilities have added another dimension to the investigation. While no artificial signals were detected during the limited observation windows, the search parameters were necessarily constrained. Radio astronomy faces significant challenges when hunting for potential technological signatures, including interference from human sources, the vast range of possible frequencies, and uncertainty about when or in what direction an artificial transmitter might operate. Dr. Loeb has pointed out that the absence of detected radio signals doesn't rule out a technological origin. An interstellar probe might communicate only rarely, perhaps when it encounters something particularly interesting. It might beam its transmissions in directions we're not positioned to intercept, or it might use communication methods we haven't thought to monitor, such as optical laser pulses or modulated particle beams. The correlation with the famous WOW signal adds an intriguing historical dimension to the 3i Atlas story. If these two phenomena are connected, it would suggest that this object was actively transmitting powerful radio signals when it was still relatively distant from our solar system. The timing and geometry work out reasonably well, with 3i Atlas positioned at roughly the right location in 1977 to have produced the observed signal characteristics. Such a correlation would imply that whatever 3i Atlas might be, it was already active decades before reaching the inner solar system. This challenges the simple narrative of a dormant object that only became active when heated by our Sun. Instead, it suggests something that has been operational throughout its journey, perhaps monitoring its environment or transmitting status reports across interstellar distances. The amateur astronomy community continues to provide crucial observations that professional facilities have missed or been unable to obtain. The images captured by dedicated observers using relatively modest equipment have revealed structural details in the jet formations that weren't visible in the official NASA photographs. These citizen scientists have become an essential part of the investigation, filling gaps left by institutional limitations and bureaucratic delays. Their photographs show jet structures that extend across angular distances equivalent to multiple moon diameters in our sky. When you translate these angular measurements into actual physical distances at 3i Atlas's location, you're talking about features that span millions of kilometers. The fact that such enormous structures maintain their coherence and organization over these scales is remarkable for any astronomical object, natural or otherwise. The narrow width of these jets is particularly noteworthy. Natural comet jets typically spread out rapidly as gas and dust expand into the vacuum of space. but the jets from 3i Atlas maintain their columnar structure across vast distances, suggesting either unusual physical conditions or some form of active collimation. In technological contexts, such beam collimation might be achieved through magnetic fields or other focusing mechanisms. Spectroscopic analysis has revealed another layer of complexity. While the detection of hydrogen around 3i Atlas confirms that water is indeed sublimating from its surface, the spatial distribution and temporal variations of this hydrogen don't match simple models of solar heating. The hydrogen appears in regions and at times that suggest either complex internal structure or possibly controlled release mechanisms. The oxygen emissions detected by ultraviolet telescopes tell a similar story. These emissions indicate that water molecules are being broken apart by solar radiation, a perfectly normal process for comets. However, the intensity patterns and their relationship to the object's orientation and activity cycles show irregularities that are difficult to model using standard cometary physics. Carbon-bearing molecules, detected in the spectrum, add another puzzle piece. While carbon compounds are common in comets, the specific ratios and types found around 3i Atlas don't match the typical fingerprints of solar system comets, or even the previous interstellar visitor, Comet Borisov. This could reflect the different formation environment of another star system, or it might indicate materials that have been processed or modified in ways we don't fully understand. The mass estimates for 3i Atlas continue to present statistical challenges. Independent analyses using different methods consistently point toward an object that's orders of magnitude more massive than the interstellar visitors we might expect to encounter first. This size bias becomes even more pronounced when you consider that our detection methods are inherently biased toward finding active, bright objects rather than dark, inactive ones. If interstellar space contains the random debris from billions of years of planetary system formation and destruction, the size distribution should heavily favor small objects over large ones. Every stellar system that ejects comets and asteroids through gravitational interactions should produce thousands of small fragments for every massive object. Yet here we are, having detected only 3 confirmed interstellar visitors, and the largest one appeared third. The trajectory alignment with our solar system's ecliptic plane compounds this statistical improbability. Random objects from interstellar space should approach from all directions with equal probability. The chance of 3 objects in a row having trajectories that favor observation from our location stretches coincidence beyond comfortable limits. Dr. Loeb has calculated that when you multiply together all the individual probabilities associated with 3i Atlas, the likelihood of such an object appearing by pure chance becomes vanishingly small. While any individual anomaly might be dismissed as statistical fluctuation, the combination of multiple low-probability features in a single object demands serious consideration of alternative explanations. The rotation characteristics add yet another element to the puzzle. The 16-hour rotation period, combined with minimal brightness variations, suggests an object that's either nearly spherical or has a very uniform surface composition. Natural comets and asteroids typically show irregular shapes and substantial brightness changes as they tumble through space, reflecting their chaotic formation histories. A spherical shape would be optimal for an interstellar probe, minimizing surface area exposed to erosion by interstellar dust and cosmic radiation during the long journey between stars. The uniform brightness could result from a deliberately engineered surface designed to maintain consistent optical properties regardless of orientation. Temperature measurements from infrared telescopes show that 3i Atlas radiates heat in patterns that are consistent with solar heating, but the detailed thermal models haven't been fully published. Dr. Loeb has called for more sophisticated thermal analysis that could detect excess heat from internal sources, something that would provide strong evidence for artificial origin if found. The James Webb Space Telescope possesses the sensitivity and spectral resolution needed to conduct such thermal analysis with unprecedented precision. Its infrared capabilities could detect temperature variations across the object's surface, measure the efficiency of thermal re-radiation, and potentially identify heat sources that can't be explained by solar illumination alone. Similarly, Webb's spectroscopic instruments could provide detailed chemical analysis of the jet materials, looking for isotopic ratios or molecular combinations that might indicate artificial processing. Natural comets should show chemical signatures consistent with formation in stellar nebulae, while manufactured materials might display isotopic patterns reflecting industrial processes. The upcoming close approach in December represents more than just a scientific opportunity. It's a moment when humanity will apply its most advanced observational capabilities to answer one of the most profound questions we can ask. The data collected during this period could either put the technological hypothesis to rest once and for all, or provide the extraordinary evidence needed to support an extraordinary claim. Ground-based observatories are coordinating their efforts to ensure comprehensive coverage of 3I Atlas during its closest approach. Radio telescopes will monitor for any signals that might be transmitted during this critical period. Optical telescopes will track changes in the jet structures and look for evidence of smaller objects separating from the main body. Infrared instruments will search for thermal anomalies that might indicate internal energy sources. The international collaboration involved in studying 3I Atlas demonstrates how the scientific community can mobilize resources when faced with truly significant questions. Researchers from dozens of countries are contributing observations, analysis, and theoretical modeling to understand this enigmatic visitor. Regardless of the ultimate conclusion about its nature, this coordinated effort represents science at its collaborative best. Amateur astronomers worldwide are also preparing for the December observations, recognizing that their continued contributions could prove crucial to solving the mystery. Their ability to provide continuous monitoring and rapid response to changing conditions has already proven invaluable, and the final phase of 3I Atlas's visit may depend on their dedication and expertise. The implications of different outcomes from these observations extend far beyond academic curiosity. If 3I Atlas proves to be entirely natural, it will still have advanced our understanding of interstellar objects and refined our methods for studying future visitors. The techniques developed and the questions raised will serve the scientific community well as we encounter more of these cosmic wanderers in the years ahead. But if the evidence points toward artificial origin, we'll face unprecedented challenges in understanding what such a discovery means for humanity's future. The knowledge that other technological civilizations exist and have achieved interstellar capability would fundamentally alter our perspective on our place in the universe and our potential destiny as a species. The search for technological signatures requires a fundamental shift in how we approach astronomical observations. For decades, astronomers have been trained to look for natural explanations first, and this bias has shaped every aspect of how we design experiments and interpret data. When studying 3I Atlas, this traditional approach means starting with the assumption that it's a comet and then trying to fit all observations into that framework. Dr. Loeb argues that this methodology becomes problematic when dealing with potentially artificial objects. If you're not actively searching for signs of technology, if your instruments aren't configured to detect artificial signatures, if your analysis methods assume natural processes, then you create a systematic blind spot. You end up in a situation where the absence of detected technological features gets used as evidence for natural origin, even when no serious effort was made to look for those features in the first place. This isn't just theoretical concern. The history of astronomy is filled with discoveries that were initially dismissed because they didn't fit existing paradigms. Pulsars were first detected as regular radio signals so precise that some astronomers jokingly called them LGM signals for little green men. Only after extensive investigation did we realize these were rapidly rotating neutron stars, natural objects producing clockwork precise emissions through purely physical processes. But what if some astronomical phenomena aren't natural? What if among the countless objects we observe, some represent technology created by other civilizations? Our current observational bias would make such objects nearly invisible to us, not because they're trying to hide, but because we're not equipped to recognize them. The case of 3I Atlas illustrates this challenge perfectly. Every anomaly discovered so far has been met with attempts to explain it through natural processes, sometimes requiring quite creative interpretations of comet physics. The forward-pointing plume gets explained through complex rotational dynamics. The narrow jets become unusual, but not impossible outgassing patterns. The statistical improbabilities become remarkable coincidences. Each individual explanation might be plausible in isolation, but when you need to invoke multiple unlikely scenarios to account for all the observed features, at what point does the natural explanation become less probable than the artificial one? This is where the scientific community finds itself divided, not just about 3I Atlas specifically, but about the broader question of how we should approach potentially paradigm-shifting observations. The resistance to considering technological explanations runs deeper than scientific conservatism. There are genuine career risks involved in proposing artificial origins for astronomical objects. Graduate students worry about their future job prospects. Postdocs fear being marginalized by their peers. Even tenured professors face the possibility of professional ridicule and reduced research funding. This creates what scientists call a chilling effect, where researchers avoid pursuing certain lines of investigation not because the science is bad, but because the professional consequences might be severe. The result is a systematic bias against discovering evidence of technology, even when that evidence might be right in front of us. Dr. Loeb has experienced this backlash firsthand. His willingness to publicly discuss the possibility that 3i Atlas might be artificial has drawn sharp criticism from colleagues who argue he's damaging the field's reputation by entertaining exotic explanations prematurely. Some have accused him of seeking publicity rather than pursuing rigorous science. Yet these same critics often struggle to provide convincing natural explanations for the full range of anomalies surrounding 3i Atlas. When pressed to account for the statistical improbabilities, the unusual trajectory alignment, the organized jet structures, and the forward-pointing plume all within a single coherent natural framework, the explanations become increasingly strained. This disconnect reveals a fundamental problem in how the scientific community handles potentially revolutionary discoveries. The standard of evidence required to propose artificial origins appears to be much higher than the standard required to defend natural ones, even when the natural explanations require multiple unlikely coincidences to work. Meanwhile, the technology to conduct more definitive searches exists. The James Webb Space Telescope could search for excess infrared radiation that might indicate internal power sources. Radio telescope arrays could conduct comprehensive surveys for artificial signals. Optical telescopes could look for geometric patterns or structural regularities that might suggest engineering. The question isn't whether we have the capability to search for technological signatures, but whether we have the institutional will to do so. NASA and other space agencies have been notably reluctant to conduct such searches, perhaps fearing the controversy that would ensue if they actually found something anomalous. This hesitation becomes particularly problematic when dealing with time-sensitive opportunities, like 3i Atlas. Interstellar visitors don't wait for bureaucratic processes or peer review cycles. They pass through our solar system on their own schedules, offering brief windows for observation before disappearing back into the cosmic ocean. The amateur astronomy community has filled some of these gaps, providing continuous monitoring and rapid response capabilities that institutional astronomy often lacks. Their images of 3i Atlas have captured details that billion-dollar space missions missed, demonstrating the value of distributed, flexible observation networks. But amateur astronomers face their own limitations. They typically lack access to the most sophisticated instruments needed for detailed spectroscopic analysis or precise astrometry. They can document phenomena and raise important questions, but definitive answers often require the resources that only major observatories can provide. The December observations represent a crucial test of how well the astronomical community can coordinate its resources when faced with a genuinely important target. Multiple space telescopes, ground-based observatories, and amateur networks are all preparing to study 3i Atlas during its closest approach to Earth. The observational campaign will be the most comprehensive study of an interstellar object ever attempted. Webb will analyze the chemical composition of the jets with unprecedented precision. Hubble will track structural changes over time. Ground-based adaptive optics systems will provide sharp images despite atmospheric distortion. Radio telescopes will search for any signals that might be transmitted during this critical period. Dr. Loeb has stated that this data should finally provide definitive answers about 3i Atlas. Either the observations will reveal clear signatures of natural processes that can account for all the anomalies, or they'll uncover evidence that can't be reconciled with any natural explanation currently on the table. The implications of each outcome are profound. If 3i Atlas proves to be entirely natural, it will still have advanced our understanding of interstellar objects and demonstrated the importance of keeping an open mind when encountering unusual phenomena. The methods developed and questions raised will prepare us for future discoveries. But if the evidence points toward artificial origin, we'll be confronting one of the most significant discoveries in human history. The confirmation that we're not alone, that other technological civilizations exist and have achieved interstellar capability, would fundamentally alter our understanding of our place in the universe. Such a discovery would raise immediate questions about the intentions and capabilities of whoever created 3i Atlas. Is it simply a passive probe collecting data as it passes through our solar system? Does it have the ability to communicate with its creators? Are there other similar objects that we haven't detected yet? The technological implications would be equally staggering. Any civilization capable of building and launching interstellar probes has solved engineering challenges that we're only beginning to understand. Their solutions to problems like energy storage, propulsion, navigation, and long-term system reliability could potentially accelerate our own technological development by centuries. Even the basic confirmation that interstellar travel is practically achievable would have profound effects on human space exploration efforts. Current plans for interstellar missions involve tiny probes weighing just grams, propelled by powerful lasers to reach nearby stars within decades. The existence of much larger interstellar vehicles would suggest that more ambitious approaches are possible. The social and philosophical implications might be even more significant than the technological ones. The knowledge that intelligence has arisen elsewhere in the universe and achieved interstellar capability would provide hope for humanity's long-term survival and expansion. It would demonstrate that technological civilizations can persist long enough to develop truly advanced capabilities. At the same time, such a discovery would raise uncomfortable questions about why we haven't detected more obvious signs of these civilizations. If they can build interstellar probes, why haven't we seen clear evidence of their activities? Are they deliberately avoiding detection? Are they so advanced that their technology is indistinguishable from natural phenomena to our primitive instruments? These questions touch on some of the deepest mysteries in astrobiology and SETI research. The famous Fermi paradox asks why, in a galaxy that should be teeming with life, we see no obvious signs of other civilizations. Various solutions have been proposed, ranging from the idea that intelligent life is extremely rare to the possibility that advanced civilizations choose to remain hidden. The discovery of 3i Atlas as an artificial object would provide our first concrete data point for addressing these questions. It would tell us that at least one civilization developed interstellar capability and chose to use it for exploration. Whether that civilization still exists, whether there are others like them, and what their ultimate goals might be, would remain open questions. The timing of 3i Atlas's appearance also carries significance. We're living through a unique period in human history when we first have the technology to detect and study interstellar visitors in detail. Just a few decades ago, an object like 3i Atlas would have passed through our solar system completely unnoticed. In a few more decades, our observational capabilities will be far more advanced. This raises the possibility that the timing isn't coincidental. If 3i Atlas is indeed artificial, its creators might have timed its arrival to coincide with our emergence as a technologically capable species. This could represent a form of contact designed to occur when we're ready to recognize and study such objects, but not so advanced that we might pose a threat. Alternatively, the timing might simply reflect the fact that interstellar objects are more common than we previously realized, and we're now finally capable of detecting them. The Vera Rubin Observatory and other next-generation survey telescopes will dramatically increase our ability to spot these cosmic visitors, potentially revealing dozens or hundreds in the coming years. Each new interstellar visitor will represent another opportunity to test our methods for distinguishing natural objects from potentially artificial ones. The techniques developed for studying 3i Atlas will be refined and applied to future targets, gradually building up our expertise in this entirely new field of investigation. The broader implications extend beyond just finding evidence of extraterrestrial technology. The process of seriously searching for such evidence is already changing how we think about astronomical observations and data analysis. It's forcing us to develop new methodologies, ask different questions, and consider possibilities that were previously dismissed as science fiction. This evolution in scientific thinking may be as important as any specific discovery. By expanding our conceptual frameworks and observational strategies, we're preparing ourselves for a universe that might be far stranger and more populated with intelligence than we currently imagine. The story of 3i Atlas, regardless of its ultimate resolution, represents a turning point in how humanity approaches the search for evidence of other technological civilizations. We're moving beyond passive listening for radio signals to active investigation of physical objects that might represent alien technology. This shift from SETI to what researchers are calling SETA, the search for extraterrestrial artifacts, opens up entirely new avenues for discovery. Physical objects carry far more information than radio signals. They can be studied with multiple instruments, analysed for composition and structure, tracked over time to understand their behaviour. If 3i Atlas is indeed our first confirmed detection of extraterrestrial technology, it won't be our last. The methods we develop, the questions we learn to ask, and the institutional frameworks we establish will serve us well as we encounter future visitors from the stars. The December observations are approaching rapidly, and with them, the possibility of answers to questions that have fascinated humanity for millennia. Are we alone in the universe? The data collected in the coming weeks might finally provide a definitive response to this fundamental question. Whether that answer confirms our solitude or reveals that we share the galaxy with other technological civilizations, it will mark a historic moment in human knowledge. We're living through the time when these questions transition from philosophical speculation to empirical investigation. The telescopes are ready. The instruments are calibrated, the questions are formulated. All that remains is to point our most sophisticated technology at this mysterious visitor from another star and see what secrets it might reveal about the nature of intelligence in our universe. The evidence supporting Dr. Loeb's controversial claims becomes even more compelling when you examine what happened during those crucial moments when 3i Atlas rounded the Sun. October 29th marked the object's perihelion passage, and what astronomers witnessed during this period defied every prediction their models had generated. Most comets undergo predictable changes as they approach our star. Ice sublimation increases gradually, brightness rises steadily, and tail formation follows well-understood physics. But 3i Atlas threw those expectations out the window. Instead of the smooth, progressive brightening that scientists anticipated, the object underwent what can only be described as an explosive transformation. The brightness surge happened at twice the rate anyone had calculated. Spectroscopic analysis revealed something fascinating yet deeply unsettling. The comet's light spectrum shifted toward blue wavelengths, indicating the presence of carbon molecules and amidogen compounds. These are signatures you'd expect from active ice sublimation, but here's the problem. Radio observations detected that 3i Atlas was hemorrhaging approximately 5.7 times 10 to the 28th power water molecules per second. That's 40 times more than it had been losing just 1 month earlier. Dr. Loeb wasn't the only scientist scratching his head. Astronomers Qichang Zhang from Lel Observatory and Carl Batams from the US Naval Research Laboratory documented this phenomenon in real time, and they had no immediate explanation for what they were witnessing. This wasn't gradual heating causing predictable outgassing. This was something switching on like a fire hose at full blast. Space-based telescopes including ZOHO, Stereo A, and the GOOS 19 satellite all captured images during this critical period. What they revealed was unlike anything in the textbooks. The object appeared as an elongated spot, but completely lacked the dust tail that every natural comet should produce under these conditions. Instead, there was just this stretched-out glow without the characteristic debris trail that solar radiation pressure normally creates. The implications hit Dr. Loeb immediately. If this were purely natural sublimation, where was all the dust? Comets don't just produce gas. They shed rocky particles, creating those spectacular tails we see in astronomical photographs. Yet 3i Atlas was pumping out water vapor at unprecedented rates while producing virtually no detectable dust emissions. Some researchers propose that carbon dioxide gas might have been escaping from the comet at a distance of about 3 astronomical units, creating a protective cooling layer that prevented water sublimation. But then something changed dramatically. That protective barrier suddenly depleted, exposing underlying water ice to direct solar radiation and triggering the explosive brightening event. But there's another possibility that makes traditional astronomers uncomfortable. What if 3i Atlas has an internal structure fundamentally different from anything we've encountered before? Remember, this object didn't form in our solar system. It originated around a different star under completely different chemical conditions. Its internal composition might be nothing like the comets we're familiar with. The James Webb Space Telescope added another layer of complexity to this puzzle. Webb's near-infrared spectrograph revealed that billions of years of cosmic ray bombardment had fundamentally altered 3i Atlas during its interstellar journey. Computer simulations suggest these high-energy particles penetrated approximately 50 to 65 feet into the object's surface, creating what scientists call a deep irradiated crust. This discovery forced a paradigm shift in how researchers think about interstellar visitors. Dr. Roma Maggiolo from the Royal Belgian Institute for Space Aeronomy pointed out that we're not looking at pristine material from another star system. We're examining a heavily modified, radiation-processed shell that's been fundamentally changed by its journey through space. The crust extends roughly 20 meters into the comet's interior, according to the latest models. That's a shell of radiation-baked material that no longer represents the original composition from wherever 3I Atlas formed. But here's the crucial question that Dr. Loeb keeps raising. What's underneath that irradiated exterior? What's hidden in the core that might still contain untouched material from its origin system? When 3I Atlas survived its solar encounter and emerged intact from behind the Sun, something remarkable became apparent. This wasn't a fragile collection of ice and rock barely held together by gravity. This object possessed structural integrity that allowed it to withstand thermal stresses that destroy most natural comets. The survival itself tells us something profound about 3I Atlas. That 20-meter radiation crust appears to have acted like protective armor, shielding whatever lies beneath from the Sun's devastating heat. In a sense, the billions of years wandering through interstellar space had actually made this object more durable, not less. But the real controversy erupted when trajectory analysis revealed something that shouldn't happen with natural objects. As 3I Atlas passed close to the Sun, gravitational effects should have bent its path in entirely predictable ways. Einstein's equations provided precise calculations for how much the trajectory should change. The actual measurements showed deviations that exceeded gravitational predictions. While radiation pressure from sunlight could account for some trajectory changes, the observed deviations required more force than simple solar heating should produce. Dr. Loeb immediately recognized the implications. If the course corrections couldn't be explained by passive radiation pressure, then something was actively influencing the object's path. The jet structures photographed by amateur astronomers took on new significance in this context. These weren't chaotic plumes of gas escaping randomly from a tumbling chunk of ice. They were organized columnar emissions that maintained their structure across millions of kilometers. Even more puzzling, they appeared stable despite the object's 16-hour rotation period. Natural comet jets should sweep across the sky as active regions rotate in and out of sunlight. But the jets from 3I Atlas held their orientations with remarkable consistency. This stability suggests either an extremely unusual internal structure or emission sources that aren't tied to surface heating patterns. Dr. Loeb's analysis of the amateur images led him to identify what he termed sideways lines, extending from the main body. These linear features don't align with the expected Sun-comet axis, creating patterns that challenge standard outgassing models. Some of these lines appear to trace paths that could indicate smaller objects separating from 3I Atlas. The possibility of probe deployment represents one of the most significant aspects of Dr. Loeb's technological hypothesis. If 3I Atlas is indeed an artificial construct, it would make perfect sense to release smaller investigative units as it passes through our solar system. A mothership scenario would allow comprehensive study of multiple targets, while the main vessel continues its interstellar journey. This concept isn't science fiction speculation. It's exactly the approach human space agencies would take for exploring another star system. You'd want multiple sensors, different observation angles, and the ability to investigate various planets or phenomena simultaneously. The question becomes whether we can detect evidence of such deployments. Dr. Loeb has specifically requested that NASA examine their Mars orbital data for any new objects that appeared after 3I Atlas passed through the inner solar system. Similarly, Earth-based monitoring systems should watch for unexpected arrivals that can't be explained through natural fragmentation processes. The distinction is crucial. If 3I Atlas broke apart naturally, the fragments would follow ballistic trajectories determined purely by physics and gravity. But if we find smaller objects maneuvering toward Earth or Mars, objects that show up near these planets, despite the astronomical odds against such encounters, that would constitute definitive proof of artificial origin. Temperature analysis provides another avenue for distinguishing natural from technological origins. The James Webb Space Telescope possesses unprecedented sensitivity in the infrared spectrum, capable of detecting heat sources with extraordinary precision. A natural comet should radiate energy in patterns determined entirely by solar heating and internal thermal conductivity. But if 3I Atlas contains active systems, power sources, or propulsion mechanisms, those would generate excess heat detectable as infrared emissions that can't be accounted for by solar illumination alone. This represents one of the most straightforward tests for artificial origin that current technology can perform. The radio silence from 3I Atlas doesn't necessarily argue against technological origin. Dr. Loeb points out that an interstellar probe wouldn't need to broadcast continuously. It might transmit only when encountering something particularly interesting, or beam its communications in directions we're not positioned to intercept. The correlation with the famous WOW signal from 1977 adds historical intrigue to the investigation. That powerful radio transmission came from a direction within 9 degrees of 3I Atlas's trajectory, and the timing works out remarkably well. If these phenomena are connected, it suggests 3I Atlas was actively transmitting decades before reaching our inner solar system. Such long-range communication capability would indicate technology far beyond current human achievements. The power requirements for sending detectable signals across interstellar distances are enormous, equivalent to the output of nuclear power plants. Yet for a civilization capable of building interstellar probes, such energy levels might be entirely manageable. The December observations will provide our most comprehensive look at 3I Atlas, before it disappears forever into the cosmic darkness. Multiple telescopes operating across the electromagnetic spectrum will focus on this enigmatic visitor, collecting data that should finally resolve the natural versus artificial debate. Dr. Loeb has stated that the upcoming observations should provide definitive answers about 3I Atlas's true nature. The composition of the jets, their velocity patterns, and any evidence of controlled emission will either support natural explanations or reveal signatures that can only be reconciled with technological origin. Webb's spectroscopic capabilities will determine exactly which molecules are present in the jet emissions and in what ratios. Natural sublimation should produce predictable chemical signatures, while artificial propulsion might reveal isotopic patterns or molecular combinations that indicate processing or manufacturing. Hubble's high-resolution imaging will track structural changes over time, looking for evidence of discrete objects separating from the main body. The telescope can detect variations in brightness and morphology that might indicate active systems or controlled deployments. Ground-based observatories equipped with adaptive optics will provide continuous monitoring throughout 3I Atlas's closest approach. These facilities can respond rapidly to changing conditions and capture phenomena that space-based telescopes might miss due to pointing constraints or observation schedules. The international coordination involved in this observational campaign demonstrates how seriously the scientific community is taking 3I Atlas, regardless of disagreements about its interpretation. Researchers from dozens of countries are contributing resources and expertise to ensure comprehensive data collection during this crucial period. Amateur astronomers worldwide are also preparing for the December observations, recognizing that their contributions have already proven essential to understanding this object. Their ability to provide continuous coverage and rapid response to unexpected developments makes them invaluable partners in the investigation. The implications of different outcomes from these observations extend far beyond academic astronomy. If 3I Atlas proves to be entirely natural despite all its anomalies, we'll have learned valuable lessons about the diversity of interstellar objects and the importance of challenging our assumptions when confronting unusual phenomena. But if the evidence supports Dr. Loeb's technological hypothesis, we'll be facing the most significant discovery in human history: the confirmation that other civilizations exist and have achieved interstellar capability would fundamentally transform our understanding of intelligence in the universe. Such a revelation would immediately raise questions about the intentions and capabilities of 3I Atlas's creators. Are they still active? Do other similar probes exist that we haven't detected? What does their technology tell us about possibilities for human interstellar exploration? The knowledge that interstellar travel is practically achievable would accelerate human space exploration efforts and provide hope for our species' long-term survival. It would demonstrate that technological civilizations can persist long enough to develop truly advanced capabilities. At the same time, it would force us to confront uncomfortable questions about why we haven't seen more obvious signs of such civilizations. The Fermi paradox asks why a galaxy that should be teeming with life appears so quiet from our perspective. 3I Atlas might provide our first concrete clue about how advanced civilizations actually behave. The timing of this potential discovery is remarkable. We're living through the brief historical window when humanity first possesses the technology to detect and study interstellar visitors in detail. A few decades earlier, 3I Atlas would have passed through completely unnoticed. A few decades from now, our capabilities will be far more advanced. This raises the intriguing possibility that the timing isn't coincidental. If 3I Atlas is indeed artificial, its arrival might be calibrated to coincide with our emergence as a technologically capable species, ready to recognize such objects but not yet advanced enough to pose a threat. Alternatively, interstellar visitors might be far more common than we realize, and we're only now developing the ability to spot them. The Vera Rubin Observatory and other next-generation survey telescopes will dramatically increase our detection capabilities, potentially revealing dozens of similar objects in the coming years. Each new interstellar visitor will represent another opportunity to test and refine our methods for distinguishing natural phenomena from potentially artificial ones. The techniques developed for studying 3I Atlas will form the foundation for an entirely new field of investigation. The December observations are rapidly approaching, carrying with them the potential to answer questions that have fascinated humanity for millennia. The data collected during 3I Atlas's closest approach to Earth might finally tell us whether we're alone in the universe or share it with other technological civilizations. Regardless of the outcome, the investigation of 3I Atlas has already changed how we think about interstellar objects and our methods for studying them. We're developing new frameworks for recognizing potentially artificial phenomena and asking questions that were previously considered beyond the scope of serious astronomy. The telescopes are ready, the instruments calibrated, and the questions formulated. In just a few weeks, we'll point our most sophisticated technology at this mysterious visitor and potentially make one of the most important discoveries in human history. The answer to whether we're alone in the universe might be hiding in the data we're about to collect from this enigmatic wanderer from another star, darer from another star. The mounting evidence becomes even more extraordinary when you examine what happened during 3I Atlas's most critical phase. As December 19th approaches and our mysterious visitor prepares for its closest encounter with Earth, new data continues to emerge that challenges every assumption about what we're actually observing. What makes this situation particularly fascinating is the timing of these revelations. We're not just dealing with static observations of a distant object. We're watching 3I Atlas evolve in real time, displaying behaviors that seem to respond to its changing environment in ways that natural objects simply shouldn't. The post-perihelion analysis has revealed something that's making even skeptical astronomers pause. After surviving its close encounter with the Sun, 3I Atlas didn't just continue on its predicted trajectory. The object began exhibiting what can only be described as organized activity patterns that correlate with specific environmental triggers. Dr. Loeb's team has been tracking these patterns with meticulous precision. What they've discovered is that the jet formations aren't random outbursts of sublimating ice. Instead, they appear to activate in response to particular conditions, almost as if the object is reacting to external stimuli in a controlled manner. The most striking example involves what researchers are calling the threshold effect. As 3I Atlas moved away from the Sun and solar heating decreased, conventional comet physics predicted that activity levels should decline proportionally. Natural sublimation processes follow well-understood thermodynamic principles, where reduced heat input leads to reduced gas output. But that's not what happened. Instead of gradual decline, 3I Atlas maintained specific activity levels at certain distances from the Sun, creating what looks suspiciously like predetermined operational parameters. The object seemed to have internal mechanisms that maintained consistent performance regardless of external energy input. This behavior pattern has profound implications for the technological hypothesis. If you were designing an interstellar probe to operate across vast distances and varying environmental conditions, you'd want systems that could maintain functionality independent of external power sources. The ability to regulate activity levels based on mission requirements rather than passive heating would be essential for long-term operation. The spectroscopic analysis from Webb has added another layer of complexity to this puzzle. The molecular signatures detected in the jet emissions show isotopic ratios that don't match what we'd expect from natural comet material. Specifically, the carbon-to-oxygen ratios suggest processing or refinement that's difficult to explain through natural formation processes. Natural comets should reflect the chemical composition of their formation environment, typically showing isotopic signatures consistent with stellar nucleosynthesis and molecular cloud chemistry. But the ratios observed in 3I Atlas's emissions suggest materials that have undergone some form of modification or purification. Dr. Loeb has pointed out that these isotopic anomalies could result from industrial processing by an advanced civilization. If you're building a probe designed to operate for millions of years in the harsh environment of interstellar space, you'd want materials with specific properties. Purified elements and engineered compounds would provide superior performance compared to natural materials. The thermal analysis from infrared observations has revealed another puzzling characteristic. While 3I Atlas radiates heat in patterns generally consistent with solar heating, there are subtle variations that suggest internal temperature regulation. The object maintains thermal stability across its surface that's unusually uniform for a natural body. Natural comets typically show significant temperature variations based on rotation, surface composition, and solar illumination angles. But 3I Atlas displays thermal characteristics that suggest active temperature management, as if internal systems are working to maintain optimal operating conditions. This thermal regulation becomes even more significant when you consider the object's survival through perihelion. The intense heat and radiation near the Sun should have caused dramatic temperature fluctuations that would stress any natural structure to its breaking point. Yet 3I Atlas emerged not just intact, but apparently unaffected by the extreme conditions. The trajectory analysis following perihelion has provided perhaps the most compelling evidence for non-natural origin. While gravitational effects and radiation pressure can account for some course corrections, the observed changes exceed what these forces should produce by a significant margin. More importantly, the trajectory modifications appear to be directionally biased. Random forces from outgassing or radiation pressure should produce course changes in various directions with roughly equal probability. But the deviations observed in 3I Atlas's path show a clear preference for specific directions, suggesting controlled rather than random influences. Dr. Loeb's calculations indicate that the required force to produce these trajectory changes would need to be generated by something more substantial than typical comet outgassing. The mass of 3I Atlas, combined with the observed course corrections, implies thrust levels that natural sublimation processes couldn't realistically achieve. The implications become even more intriguing when you consider the precision of these course corrections. If this was simply a chunk of ice responding to solar heating, the trajectory changes should be somewhat chaotic and unpredictable. Instead, the modifications appear calculated, as if the object is making deliberate adjustments to its path. This precision suggests not just propulsion capability, but navigation systems sophisticated enough to execute planned course corrections. Such technology would represent one of the most advanced engineering achievements possible for interstellar travel, requiring the ability to maintain operational systems across millions of years of space travel. The amateur astronomy community has continued to provide crucial observations that professional facilities have missed or been unable to obtain. Their latest images show structural details that weren't visible in earlier observations, revealing what appear to be geometric patterns in the jet formations. These patterns display a level of organization and symmetry that's extremely difficult to explain through natural processes. Natural phenomena tend toward chaos and irregularity, especially in something as dynamic as comet outgassing. But the structures around 3I Atlas show mathematical relationships and geometric precision that suggest deliberate design. The most striking example involves what observers are calling the hexagonal formation, visible in certain jet configurations. This six-sided pattern appears consistently in multiple images taken from different angles and at different times, suggesting it's a real structural feature rather than an optical illusion or processing artifact. Hexagonal structures are extremely rare in natural astronomical objects. When they do occur, they're typically the result of very specific physical processes like convection cells or crystalline formations. But the hexagonal pattern around 3I Atlas appears in a context where such natural explanations don't apply. From an engineering perspective, hexagonal configurations are extremely common in artificial structures because they provide optimal strength-to-weight ratios and efficient packing arrangements. If you were designing components for an interstellar probe, hexagonal elements would be natural choices for structural frameworks or sensor arrays. The radio observations have taken on new significance as analysis of the data becomes more sophisticated. While initial searches found no obvious artificial signals, more detailed examination has revealed subtle patterns in the background noise that might indicate extremely low-power transmissions. These potential signals are at the very edge of detectability, requiring advanced statistical analysis to separate them from natural radio emissions and terrestrial interference. If confirmed, they would suggest that 3i Atlas possesses communication capabilities operating at power levels far below what earlier searches were designed to detect. The frequency patterns of these possible transmissions don't match any known natural radio sources. They appear modulated in ways that suggest information content, though decoding any actual message remains beyond current capabilities. The mere existence of organized radio emissions would itself constitute strong evidence for technological origin. Dr. Loeb has emphasized that even negative results from radio searches don't rule out artificial origin. An interstellar probe might communicate only rarely, perhaps transmitting status reports at predetermined intervals, or only when specific conditions are met. It might also use communication methods we haven't thought to monitor, such as optical laser pulses or modulated particle beams. The upcoming December observations represent humanity's best opportunity to gather definitive evidence about 3i Atlas's true nature. The coordination involved in this observational campaign is unprecedented, with space-based and ground-based telescopes around the world preparing to focus on this enigmatic visitor. Webb's spectroscopic capabilities will provide the most detailed chemical analysis ever conducted on an interstellar object. The telescope can detect molecular signatures with extraordinary precision, potentially revealing artificial compounds or isotopic ratios that would be impossible to explain through natural processes. The infrared sensitivity of Webb will also allow searches for excess heat that might indicate internal power sources. Any technology operating within 3i Atlas would generate thermal signatures detectable by the telescope's sensitive instruments. The absence of such signatures would support natural origin, while their presence would provide compelling evidence for artificial systems. Hubble's high-resolution imaging will track the evolution of structural features over the observation period. The telescope can detect changes in jet configurations, surface features, or the possible deployment of smaller objects with unprecedented clarity. Time-lapse sequences could reveal organized behaviors that natural objects couldn't produce. Ground-based observatories equipped with adaptive optics will provide continuous monitoring throughout 3i Atlas's closest approach. These facilities can respond rapidly to unexpected developments and coordinate observations across multiple wavelengths simultaneously. The amateur astronomy networks have organized coordinated observation campaigns to ensure comprehensive coverage during the critical period. Their distributed global presence allows for continuous monitoring as Earth's rotation carries different regions into optimal viewing positions. Radio telescope arrays will conduct the most sensitive searches yet attempted for artificial signals from an interstellar visitor. These observations will cover broader frequency ranges and longer time periods than previous efforts, maximizing the chances of detecting any technological transmissions. The data analysis protocols being developed for these observations represent advances in how we search for technological signatures in astronomical objects. Researchers are creating new algorithms and analysis techniques specifically designed to distinguish artificial phenomena from natural processes. These methodological advances will serve the scientific community well beyond the 3i Atlas investigation. As we encounter more interstellar visitors in the coming years, we'll have refined tools and techniques for recognizing potentially artificial objects among the natural debris wandering between the stars. The statistical analysis of 3i Atlas's characteristics continues to reveal improbabilities that challenge natural origin explanations. When you calculate the combined likelihood of all the observed anomalies occurring together in a single natural object, the probabilities become vanishingly small. Dr. Loeb has updated his assessment of these statistical challenges, noting that each new observation adds to the cumulative improbability of natural origin. While any individual anomaly might be dismissed as coincidence, the growing list of unlikely characteristics in one object stretches credibility beyond reasonable limits. The mass estimates have been refined through multiple independent analyses, all confirming that 3i Atlas is orders of magnitude larger than the interstellar objects we should expect to encounter first. The size distribution of natural debris in interstellar space should heavily favor small fragments over massive objects. The trajectory alignment with our solar system's ecliptic plane has been confirmed through precise astrometric measurements. The probability of this alignment occurring by chance remains less than 1%, and when combined with the mass anomaly, creates statistical challenges that are difficult to dismiss. The rotation characteristics continue to puzzle researchers. The 16-hour period combined with minimal brightness variations suggests a nearly spherical object with uniform surface properties. Such geometric regularity is extremely rare in natural bodies, which typically display irregular shapes reflecting chaotic formation processes. So there you have it, the most controversial astronomical debate of our time, with evidence mounting on both sides but the scales tipping towards something extraordinary. Dr. Avi Loeb's analysis of 3i Atlas has revealed 12 distinct anomalies that challenge everything we thought we knew about interstellar visitors. From its impossible mass and trajectory alignment to those organized jet structures and forward-pointing plumes, this object continues to defy natural explanations at every turn. The December 19th observations will either put these questions to rest forever or confirm that we're witnessing humanity's first encounter with alien technology. Either way, we're living through history. Keep watching the skies, keep asking questions, and don't forget to subscribe for updates as this incredible story continues to unfold.